In this lecture, we'll be discussing the basics of colligative properties. Let's start with the term colligative. Colligative means many, and it means, in terms of chemistry, colligative properties. It means that we're discussing the effects of how a solvent properties change with the addition of solute particles. Okay, so really it's essentially the properties of a solution and how they differ from the pure solvent. As we add more and more solute particles to a solution and the concentration increases, we notice that the solution takes on a whole set of new properties that the pure solvent doesn't have. And what's interesting about colligative properties, what's important to understand as well, is that colligative property is about really the ratio of solute to solvent molecules or particles. And as you increase this ratio, as you increase this ratio, the properties move farther away from the pure solvent and more toward a solution or something new. When you only have the solvent, we know its boiling points, we know its melting point, and all those things. We have a phase diagram that goes with the pure solvent. But as we increase the concentration of the solute particles, its new properties become something brand new and different, and very important as well. But again, colligative properties is the ratio of the solute to solvent particles, but more importantly, it has nothing to do and does not care about the identity. So these solute particles, although can be different, as long as they're soluble, which means they interact and have very similar attractive forces that the solvent has, as long as they're soluble, or sometimes you hear the word miscible, and there's an interaction between the solvent and solvent, we will have these types of properties no matter what the identity. So no matter if we're adding, let's say, ions, in the case of, let's say, sodium chloride we know is soluble, okay, and we know it dissociates into Na plus and Cl negative, and we write aqueous to show that dissociation. Now, these are called electrolytes. Things that are salts that are soluble are called electrolytes. Now, why are they called electrolytes? Well, because free ions in solution can conduct a charge, all right, as we've talked about. Now, whether they are ions or they are molecules, they're solute particles. For instance, we could take glucose, C6H12O6, and it's a polar molecule, and we could take solid glucose and we can dissolve it in water. It's a physical process, and it will become aqueous glucose. And that also will make something called a solution. We should all know that a solution is when you have a dissolved solute by the solvent, and we denote a solution by these aqueous. An aqueous solution is when you have, of course, the solvent, the water solvent, doing the hydration, or solvation as sometimes we will use. Now, of course, the solution is homogeneous. Homogeneous solutions, or I should say homogeneous mixture, is what a solution is. So if we've got solute particles that could be big or small, ions or molecules, it does not matter what the identity is. The bottom line is how many. That's very important. How many? Because the more solute particles you have, again, the greater the change in the properties. So the question is not what, but how many particles. And that's why you'll see in this area we use something called molality a lot, but we also could use mole fraction. How many more moles are we added? What is the molality of the solution? So it's very important that we understand that. Okay, and that's the basics. Now, let's go look at the phase diagram of a pure solvent like water. Okay, as we've discussed this already, we know where the different places are. We know this is pressure, we know this is temperature, and the triple point. And then we, of course, up here somewhere, we've got the critical point. But what's really important is that we know that the normal boiling point of, let's say, water is 100. Normal means that it's at 1 atmosphere of pressure, or standard pressure, I should say. 1 atmosphere of pressure, 760 torr, 760 millimeters of mercury, 14.7 pounds per square inch. There are a lot of equivalents. But if we're at normal pressure, we know that we boil at 100, and at normal pressure, we freeze at 0. We're also aware that these temperatures are not static. You change the pressure, you change these temperatures. Now, this is, of course, for a pure solvent. And this is a static scenario. Water can be identified, it's an intensive physical property, by these static temperatures at this known or normal pressure. Now, what's interesting to note is that when we add solute particles into the solution, what we get is a very classic vapor pressure lowering. And this curve right here, this vapor pressure curve, I like to call because it denotes the change, okay, of, let's say, the new temperature at which it boils. For instance, we know that this curve here, if you were to lower the pressure downward from 760 and we go across, we're going to boil at a lower temperature. And if we have a higher pressure, above 760, we would boil at a greater temperature. So we know that. But when we add solute particles from a pure solvent, the vapor pressure is lowered. And we call it Raoult's law. And it's something we've already discussed. Let's talk about why this happens again. Well, if you've got a container and you've got your water molecules, and for all intents and purposes, we'll make the water molecules blue. Water's blue, right? No, of course not. Any case, here's my blue molecules. My water molecules should all look the same, but hey. All right. And then I've got my solute particles. My solute particles are the dissolved solvent. The dissolved solute particles, that could be ions or molecules, it's not going to matter. But we will notice something. These solute particles, okay, will physically get in the way of water trying to evaporate. So when you had a container with no solute particles in them, just solvent particles, when water gets enough energy, it can overcome its H bonds, its intermolecular attraction with itself, and get to the surface, right? It can release as a gas molecule, and that's the vapor pressure upward that we talk about. Boiling is when, of course, the pressure downward, okay, by the atmosphere is equal to the vapor pressure that pushes up from the surface of a liquid. That's what boiling is. So we know that when the vapor pressure rises, we boil that way. Well, if you put solute particles in here, water still has to overcome its attractive forces, but it's got to get to the surface. And these solute particles get in the way. They're like not only a distraction, but a physical barrier. So it's harder for the molecules to do that. And what happens is the amount of evaporation is less. The amount of vapor pressure is less. So if you used to boil at 100, and now all of a sudden I'm going to lose some vapor pressure because of the solute particles getting in the way, no longer am I boiling. I need more vapor pressure upward to match the 1 atmosphere. So what's going to happen is I need more heat. Right, I need more heat to give these molecules enough energy to circumvent this obstacle and then evaporate. So with more heat, we can create more vapor pressure that equals the atmospheric pressure, and then we've got boiling. So what happens is our vapor pressure is lowered, and that's Raoult's law. We learn that the vapor pressure, the new vapor pressure, is equal to the mole fraction of the solvent times the vapor pressure in standard conditions that we get from tables. And we work that through. If the mole fraction of the solvent was 1 and there's nothing there, no solute particles, 1 times the vapor pressure in tables would be that vapor pressure. But if you add more solute particles, this fraction drops. Let's say it goes from 1 to 0.9 to 0.8, and then you take 80% of this number, you can see that this vapor pressure is going to drop. So vapor pressure dropping is a result, or one of the first colligative properties. Now, very important though, And the vapor pressure drops, okay, as we just denoted here. Take this vapor pressure away, you need more heat in order to boil. And if this line drops, you can see that my new boiling point, old boiling point was here, but my new boiling point, okay, is now right here. Right at that green dot. Hopefully that's green. Right? The vapor pressure dropped. I'm still at 760 torr or 1 atmosphere. That didn't change, but now my line dropped, my vapor pressure dropped, and now I boil, okay, at a new temperature. And the difference between here and here is my change of temperature of boiling. All right? And we call this boiling point elevation. The boiling point is elevated. Either you can see it graphically, or you can understand that you're going to need more heat to get these water molecules enough motion so they can get around and evaporate and now match the pressure pushing down. All right? Now, the amount of raising in boiling point, or the standard we have, and we have a constant, and let's talk about that, the change of temperature from boiling, okay, is equal to the molality times something called K of B. And this is called the molal boiling point constant. What it means is for every 1 molal solution, the boiling point is elevated by a certain number. And for water, KB is 0.52, and that's degrees Celsius per M. So what does that mean? For every 1 molal solution, and now little m molal means 1 mole over kilogram of solvent. So for every mole to kilogram of solvent ratio, there's an increase in the boiling point of 0.52 degrees. That's how much it goes up. Okay, and that's from boiling point elevation. We'll talk more about that. Now, we talked about in class, for those that were here, that there's a very important, okay, ramification or practice used for boiling point elevation, and that's coolant. Right? We put coolant in our coolant systems in our cars to prevent boiling. We don't want boiling. If your car is boiling, it creates gas. Gas creates pressure, and you're going to blow out a hose, and you've seen those people on the side of the road. So boiling point elevation is our very important colligative property. So we have boiling point elevation, and I can spell elevation, and its direct result from vapor pressure lowering. So we also have vapor pressure lowering, which we've already learned to be Raoult's law. So vapor pressure lowering is the new vapor pressure is equal to the mole fraction of the solvent times the vapor pressure from tables. Boiling point elevation is the change in temperature in boiling is equal to the molal, the molal concentration times the K of F, which is a constant for water or any other liquid we want, times something called the I. We'll talk about those in a second. All right, now for water, K of F, because you don't always have water in solutions, is 0.52 degrees Celsius per molal. Okay, which means for every 1 molal solution, the boiling point of the solution increases 0.52. All right, so we've already dealt with this one, and now we have the boiling point elevation. All right, now we have another factor, and before I go forward, I didn't talk about a practical use of boiling point elevation. I guess I did, and that, of course, is used in coolant. Coolant. It prevents things from boiling, so we don't have that pressure, all right, and keeps things, I wouldn't say cool, but it keeps them from boiling. And so that when we're using a liquid to go from the engine block of a car to, let's say, the radiator to get cooled, we don't want it to boil. We prevent that by adding particles, okay, usually ethylene glycol. Now we have one more that we want to get after today, and that's right here. You notice this curve drops. Notice the freezing point is right here. And let's make that a green dot. This is the freezing point of the what? Of the pure solvent. But as I add solute particles, the vapor pressure drops, as we talked about. This line drops. Now what happens is the new freezing point, okay, is where? Well, if you look at this curve, the curve drops. That means my triple point is probably going to drop as well. And what's going to happen is if my triple point drops, I'm going to make a new line, okay, trying to keeping the same type of angle to the best I could. So this curve kind of drops down, and you notice my new freezing point on my supposedly straight line is now right here. And you notice, if you guessed it, freezing point just got depressed. The difference from here to here is the change of my freezing point. All right, so change of F, or I should say change of T of F. That's what I should do here. So change of T of F. Now, if this is a 1 molal solution, this change would be 1.86 degrees Celsius per m, and this would be equal to the K of F. K of F is called the molal freezing point constant, whereas over here in B we had the KB, and let's just make the KB was the molal boiling point constant, and that was what? 0.52 degrees Celsius per molal. So these are our two constants. So if we had a 1 molal solution, this change in temperature would be 0.52, and the change of the freezing point would be 1.86. What's important to note, though, is direction. The freezing point gets depressed. It gets lowered. So we have a new colligative property. We have freezing point depression. Okay, and its formula is the change of the temperature of the freezing equals the molality times the K of F times I. I can see that I made a mistake previously, where this is the K of B. I feel bad, now I'm over it. But this is the constant that would go here. And of course the K of F, or K of, I did it twice. This is the molal boiling point constant. I can do this. KB. K of F is equal to 1.86 degrees Celsius per molal. That's how much the freezing point goes down. And that's our colligative properties. Now, some people have a difficult time understanding why the freezing point goes down. Graphically, it makes sense to some people. Other people say, well, how? Again, I have a tough time understanding how it would take a colder temperature to freeze. Well, I'm going to try to do it non-graphically for you. If you've got some things that are trying to freeze, let's destroy a container. And in this container, I've got a crystal, okay, regular geometric pattern, my blue, whatever it might be. Okay, and then I have, okay, some non-crystalline blue dots. They're just kind of haphazard. I guess this could be water. Now, let's put some. Now we know that when something melts in equilibrium, as it melts, something will freeze. So you have the rate of freezing equals the rate of melting at some point. And what happens is when you add solute particles, okay, solute particles that get into the solution, they also block the ability of this water molecule trying to refreeze. Let's say this water molecule wants to get to a certain position. Let's say that position is right here to become part of the crystal. These solute particles, these red solute particles, make it tough for that particle to try to get there. It's impeded by those. So it can't get there. And therefore, it doesn't, how can I say, refreeze. And guess what? The rate of melting is faster than the rate of freezing, and that's why you get the melting. And one way to show that is a nice little video, and let me play that for you. So let's see some water here. This water is surrounded by some ice. You can see in the crystal pattern. So let's go play this a little bit, maybe. And when we play, we see that we have some melting and we have some refreezing. Notice the melting, refreezing, we're in equilibrium. There's some freezing, melting, okay, freezing. You see some molecules, okay, doing both. Some are melting, some are refreezing. And the amount of both going on is the same. If we had a cooler with water in it, the amount of freezing and melting would be about the same, and the ice would stay forever if, of course, no heat got into the cooler. Now let's add some solute particles. Adding some solute particles, you can see that the solute particles are blocking the refreezing, and therefore the melting occurs at a faster rate. Solute particles are increasing the rate of freezing, and that's why we drop salt on ice. One of the applications of colligative properties will put salt on ice, and we make the ice melt faster. Well, why? Well, very simply, what it's doing is it's blocking the refreezing. And we also can say that it's lowering its freezing point. And another point here is that it does not have to be salt. It can be any solute particle that dissolves with water. Salt happens to be something we use because it breaks apart into more ions. Therefore, it breaks apart into more particles and has a more effective job in doing that. But clearly, okay, solute particles are blocking, inhibiting the pathway of these water molecules from trying to freeze in this scenario. Thus, melting keeps occurring. So we're back to our three main colligative properties: vapor pressure lowering, which creates boiling point elevation, which we call coolant, and freezing point depression, which, by the way, we call antifreeze. We prevent freezing. Antifreeze. Liquid that prevents freezing because we've lowered the freezing point. But I still believe there's some people who don't get why solute particles prevent the freezing. Let's talk about that some. Let's say I have ice at 0 degrees Celsius, and I have the air temperature at 0 degrees Celsius. We can all say that clearly the ice will stay a solid. Now, if the air temperature, and let's do it this way. Here's my ice, okay? What if the air temperature became 10 degrees? All right, so let's think about this. Ice is at 0. I make this 0 degrees Celsius. We have our ice here, and we have our air here initially. Let's do it like this. Okay. Now, so air and the ice are at the same temperature, and of course, it's gonna work out. The ice is gonna stay here. Now, if the air temperature goes above the ice's freezing point or melting point, depends on which direction we're talking about, and now is, let's say, 10 degrees, clearly heat will flow from hot to cold and the ice will melt endothermically, grabbing the energy, and you'll have melting. Okay, but there's another way we can move this. What if I was to lower the freezing point of ice to, let's say, negative 10 degrees Celsius? Well, now the air is still what? Higher, and you have melting. And that's what happens. By adding solute particles, you have just lowered the freezing point. So now the air temperature or the surrounding temperatures are now warmer. And now what? Heat flows from hot to cold, and we melt the ice. I don't care how you think about it, but when we put salt or solute particles on ice, by lowering the freezing point, which really means we're doing what? Blocking the refreezing, okay, the air can heat the ice. Now, there's a limit to this because there's only so much, the temperature that we can make the ice go is limited by the solubility of the compound we're adding. We can only go so low. If the air temperature is negative 50, like let's say in a cold night in Alaska, let's say over the Arctic Circle, uh, that's still going to be way too cold. Ice would be somewhere above that, and we'd have to drop the ice's temperature way below -50, and we can't do that by adding enough salt or solute particles. So there's a limit to that. But what we can do is we can have water that's below zero, not freezing, and that's what antifreeze is, and that's how it works. Okay, so freezing point depression, boiling point elevation, all result from the vapor pressure lowering of that curve. And again, how do we work with these formulas? Well, let's go back to the top and let's start talking about these formulas a little bit. Okay, well, again, if we're talking about boiling point elevation, we're going to solve for the change of temperature of the boiling, okay, is equal to the molality, which is moles of solute, the stuff being dissolved, over a kilogram of the water or the solvent. All right, that's the molality, times the constant that I'll have to give you, which we call Kb. Now for water, boiling elevation, it's 0.52, okay, degrees Celsius. So this is 0.52 degrees Celsius per molal. And you can see if you multiply this by the molality, you get a degree Celsius. And then it's timed by something called an I factor, called the Van Hoff factor. And this I helps us fix a problem we have. As I talked about earlier, some compounds dissociate into more ions. If I have a 1 molal solution of sodium chloride, don't I really have 2 moles of free ions? Because it breaks apart into these ions, and colligative properties about not what, but how many. So I have to think about how many particles are getting in the way. So to adjust for that, for something like sodium chloride, or anything that's an electrolyte or a soluble salt, we would throw a 2 in that I factor right here. So this breaks apart into 2 ions. What it really does is adjust my molality to be indicative of twice as many of that. Now, if I had something like calcium chloride, which is called ice melt, and by the way, rock salt is NaCl, ice melt is calcium chloride, this breaks apart into, you guessed it, 3 ions. You'd put a 3 here. So calcium chloride, just by the number of particles it dissociates into, this electrolyte, we would put a 3 here. And that, of course, would change my boiling point even greater. Now, it would also do what to my freezing point? It would lower my freezing point even greater. So boiling point is elevated, my freezing point is depressed. So the more particles I break apart into. So you've got to consider what you're dealing with in terms of the I factor. But if it's something molecular, like glucose, hey, you put sugar on ice, it will melt it because it'll get in the way. It won't do as well as these salts because the I factor for glucose is what? 1. You put a 1 there because glucose is a molecule. It's molecular. It doesn't break apart. So its effect on, let's say, the freezing point isn't as great, or boiling point. Bottom line, boiling point elevation, freezing point depression, what you're solving for in these formulas is the change of the boiling point. So let's go to the homework for a second, and then we'll be on your own. All right, so here are our freezing point depression formulas, which will be given to you, and your boiling point elevation formulas. Freezing point goes down, and your boiling point is elevated, all because of the solute particles getting in the way. And these are those colligative properties. Okay, so all this will be given to you. Let's do a question together. How much will the temperature increase from its boiling point of a solution of 80 grams of NaOH in 2,000 grams of water? Okay, we'll look at our formula. Our change in temperature of our boiling is equal to the molality times the K of B, which is that constant for water, times the I factor, the Van Hoff factor. So the molality, I got 80 grams of NaOH. All right, well, sodium is 23, 16 plus 1, this is 40 grams per mole. All I just did was a formula mass. So if it's 40 grams per mole, 80 grams of NaOH, getting rid of grams, grams goes in the bottom, 1 mole is equal to 40 grams. Obviously, I have 2 moles. Why do I want moles? I want molality. Molality is moles of my solute, in this case it's the sodium hydroxide, over a kilogram of water. Oh, 2,000 grams of water? That's 2 kilograms of water. So my molality, 2 divided by 2, is 1 m. So 1 m goes here. My Kb, my constant for boiling, is 0.52 degrees Celsius per molal. And because it's sodium hydroxide is a salt. It's an electrolyte. It breaks apart into Na plus and OH minus. Therefore, I've got to treat that I with a 2 here. And then, of course, we multiply this together. The I factor is a dimensionless number. So 1 times 2, 2 times 0.14, 1.04 degrees Celsius is my change in temperature of my boiling. That's how much the boiling will change. Now, if we could jump down to number 3, what will be the temperature of the boiling point from the solution in question 1? Well, the boiling point in pure water, the normal boiling point is 100 degrees Celsius. And we're going to add 1.04 degrees Celsius because it's a boiling point elevation, and my new boiling point is 101.04 degrees Celsius. So this does not solve for the new boiling point, just a change. And you have to remember, the boiling point is elevated. Okay, the freezing point is depressed. So if you do number 2, what's the temperature decrease from the freezing point? We're going to use a new formula, same thing, molality, but the constant is different for the freezing point. It goes down 1.86. I factor is still the same. All right, so if you're using the same formula, you'd plug in the 2 for the I factor. This is a different number and a 1, and you'd find the change. So let's do that. So we have the molality is still 1 m. We know that it's 1.86 degrees Celsius per m. And the I factor is 2 because it is a salt. It's an electrolyte. It breaks apart into 2 ions. It corrects for the 1 molal solution of NaOH, which we really know is a Kardashian wedding that breaks apart into 2. So we put this together. What we get is 3.72 degrees Celsius. That's my temperature, change in temperature of my freezing. It's not my new freezing point. Okay? If you go to question 4, question 4 says, what will be the temperature of the freezing point? Well, the freezing point is 0.00 degrees Celsius. So it's going to be below 0. So obviously it becomes negative 3.2 degrees Celsius, and this is the new freezing point of my solution. And that's freezing point is depressed. So please finish this front side ditto. All right, and try number 7. Okay, hope that helped a lot.